Okay, so here we go. The one identity we're learning today is called the Pythagorean identity. Make sure you put this one on a card. We are actually going to learn two other versions of this identity next week. So on the card you write this on, you should probably leave room for two other identities. And I would just have those three identities on this one card. So this is your main fundamental Pythagorean identity. Since in the next chapter you'll get the opportunity to start learning how to prove identities. Maybe that's more chapter 3. But anyway, we will get to it. I want to take every opportunity to kind of show you where things come from because you need to get in the mode of being able to do proofs. Okay? So I want to prove to you that this formula really does work. Okay? So, let's suppose we have a triangle. And I should have drawn it the other direction so that it's just like in quadrant 1 on the unit circle. Sorry. Okay, so let's say our angle alpha is right here. So if this is on our graph, what do we call this side of our triangle? It is the adjacent side, but what variable do we use for it on the graph? Okay, and then this one is y, and this is r. Or if you'd rather use a, b, and c, that also works. I'm just using the variables x, y, and r, but it doesn't really matter. If you used a, b, and c, it would be the same thing. Okay, so Pythagorean theorem. Pythagorean theorem is a squared plus b squared equals c squared, or we could use instead the letters that I've given you here, which would be what? X squared plus y squared equals r squared, correct? Right? Isn't that Pythagorean theorem? Okay. But notice how we're trying to prove this identity here. What do you notice on the right side of the identity? It equals what? 1. So we really don't want r squared on that side. We want 1 on that side. So what can we do next to this so that we can get a 1 over there? Divide both sides by r squared, right? Okay. So if I was doing this more as an official proof, I would kind of probably do it kind of in 2 columns. So you would start with something like x squared plus y squared equals r squared. And then you would divide both sides by r squared, so you have x squared over r squared plus y squared over r squared equals 1. Correct? And then you can rewrite this as x over r squared, and you can rewrite this as y over r squared. Yes? Now from our picture that we were just looking at here, remember how sine of alpha is opposite over hypotenuse, or y over r, and cosine of alpha is adjacent over hypotenuse, so x over r. So can't we just take these and substitute them in here? Okay, so substituting those in, we end up with x over r is cosine squared, and y over r is sine squared. Okay? But in trigonometry, for some reason, instead of putting it in parentheses with the square there, to save, I think it's to save writing with the parentheses. If we want to square it, we put the square here instead, and that means this. Also, for some reason, we always list sine before cosine. I don't know why that's kind of traditional. So even though this has turned out to be cosine plus sine, because I put x plus y instead of y plus x, does it really matter what order they're in? No. So since it does not matter, and since this just means this, that's just the notation, that just verified this identity using a triangle and Pythagorean theorem. Okay? So now that we've verified that, you know this is true, you should never have to do that again. Okay? So do you guys understand that sine squared alpha means sine alpha squared? And I think the reason for it is that mathematicians traditionally like to save writing. And so they try to shorten things anywhere they possibly can. And so that eliminates the use of parentheses. Because otherwise, if you just eliminated the parentheses and put it there, it would look like you were squaring the alpha. You're not squaring the alpha, you're squaring the whole thing. Okay, do you understand that notation? Okay.